Welcome back, everybody. Welcome back to the channel. So today we're going to pick up where we left off, and really quick, if you guys hear any noise, that's the fan. It's pretty hot where I am, but let's go into object-oriented. So we're going to do the object-oriented folder next. In this episode, we kind of did pretty much everything in the data folder. Now we're going to do this. So we're going to need to create a couple different classes. We're going to start with field, and fields are pretty straightforward, I think. So let me close some of these things here. And we can kind of see, so here's the imports. We just import data entity. And of course, I have a bunch of class references here for things that I referenced down below. And as usual, we have our data entity class imported as a public data entity. And we, of course, inherit all the data. So first, let's actually go down here to look at the fields. So fields are going to have a couple different things. We're going to have the key. Now, I don't remember what that is here. Let me do a quick check to see what that is and why we need it. Key. Okay, apparently that's not used. So I'm going to delete that. Let me just double check. That's kind of weird. I'm not even going to edit this out. I'm just going to leave it in. Let me just double check. Okay, I guess not. All right, we're going to need whether or not our field is an array. We're going to need whether or not our field is a null field. That's for when we're processing function calls, I believe. We're going to need a Boolean for inline check. This is for when we inline fields. So like we can have constant fields in our programming language. So we want to make sure we can inline them. We also want to say whether or not the field is a local variable. Very important. Whether or not the field has been initialized. So in our programming language, we're going to have a concept of initialization tracking, where basically if you have like a field initialized at a certain point in a function, and considering that our programming language is supporting labels, that usually mucks a bunch of things up. Like if we try to jump to something where basically a variable hasn't been initialized yet, that could cause some weird bugs and undefined behavior. We have scope level. That's basically going to represent where the variable was defined. We have initialized PC, so this is the program counter. That's what the PC is short for. And this is only used for local variables, by the way. We don't really care about when or where or why variables inside of an instance were created. We'll handle that manually. After that, we have storage locality. We've already kind of talked about that. So, is it a thread local variable or is it just a regular? Then we have pointers to methods. So of course fields are going to support getters and setters, so that's what that is. And then finally we have a pointer to our utype class. And that's it. Fields don't really have too many elements to them, so let's kind of look at a couple of functions that I have. So of course I have the standardized empty constructor, and as you can see here, I just put everything to the default value. Just make sure, again, and you're going to see this across the programming language, any address that I have is going to, or like anything that represents something tangible that can like either be an address or a point in the code, I always initialize them to invalid address, as I talked about before, which basically, yeah, it'll take me to it, which is basically this random number. And when we go to searching in our executable, we can look for that number and it'll make it very obvious if we have any bugs. But yeah, so I'm not really going to go over this. You guys can kind of copy it and pause the screen. It's pretty straightforward. Down here, we have a constructor for actually initializing a variable. So this is what we're going to be calling in our compiler and what we're mainly going to be using. So you want to pass in what's the type of the field, the GUID or the serial number. We're going to pass in the name of the field, who owns it, any access flags that the field may have, its metadata, its storage locality, and the address of the field. So the actual in-memory address. As you can see here, we basically do all the basic setup. Like we default basically most of the things to what they originally were up here, the same way we did it up there. But we, of course, want to fill in the specific fields that we are passing in here. So like, storage locality, GUID, name, address, so on and so forth. So pretty sure you can understand that. Don't really have to go too much into that. Next, we have our free. So we want to free up a field. That just calls a release, which is in the data entity, which just frees up the flags. After that, let's see, do we have any easier ones? So this is not used. I'm going to get rid of that. All right. Next, we have a toString. And this toString method is going to piggyback off of the utypes toString that we went over yesterday. So for printing a value of a field to a string, we're going to want to create a string stream, and check to see if the full name is not equal to empty. Like if we have a full name, then we want to basically say full name and then put like this colon here. And then we want to check to see if the type is equal to untyped. If so, we want to put that. If it's equal to any, then we put any. And of course, if we have a utype, if utype is not equal to null, then we basically print out whatever the utype.toString value will return. And obviously, if it's none of these, then we just say question mark and we return the string. So that's that. Next, we have equals and is related. So this is kind of similar to utypes. So basically what we want to do is just make sure that fields are basically the same. So we're going to basically check to see if the field that we're passing in, if the type is equal to any, then we return true. Because the concept of that is if you're trying to resolve a function where you're passing in this lambda and you're not specifically providing the types of every single argument, if it's any, well, it's anything. So obviously it'll match with whatever the type of this field is. After that, we want to make sure we have the same types. So if the types are the same and they're both either not an array or they're both are arrays, then we can successfully check to see if they're equals. Otherwise, obviously they're not, so we just return false. Then we check to see if the current type of the field that we're in is a class. If so, then we try to check to see if the utype is not equal to null. We check to see if the field we're passing in is not equal to null for its utype. And then we want to basically just check to see if the types are the same. And then we basically, and the reason why I want to do that too, by the way, is like we don't know what like type of the field this is, right? So this field could have a function pointer for all we know, right? But if we know that the U types are exactly the same, then we know we're comparing the same data structure. And obviously, because if the type is a class, then I mean, if this is also a U-type class for field, then we know we can, cast it successfully. So all we do is we just cast both the current U-type and the field U-type as a class object and call match. We've already seen that function and what that does, so that's straightforward. After that, we have this function pointer here. So here's what makes it easy, right? If we know the types are the same and we know like the array is like they're both either are arrays or not arrays, and if it's not a function pointer, we just return true, right? Because obviously, either they're both vars or something else. But if they're a function pointer, then we, get the method here of the utype. And actually, this was dated before I created the get method function. Get method, I just say, utype get method, and then we basically want to get the compare function or the function that we're going to compare and check the function type. So we haven't gone over this yet, but functions have, whoops, go back. We have several different function types. So here, I guess I'll just kind of show it now. So we have several different types of functions. So for each function, we have normal functions, which is just like a foo function. You define foo and you just put stuff in there. We have constructors for classes. We have pointers, which represents if you create a function pointer to point to something else. We have lambdas. We have operator overloads, delegates, which are functions that delegate work to other classes. And then, of course, we just don't know what the function is. So let's go back. So now we have our utype check. So we check to see if, the utype of this function is not equal to null. And what this is this is the return type of the function. So in the same vein how fields have utypes, this represents the type of the field. Functions also have utypes, which represent what the function is going to return. So this is in a sense like the type of the function. Um, so we check to see if that's not equal to null. If so, then we check to see if the current utype is equal to null, which that's not necessary. But then we check to see if the field's utype is not equal to null. And we want to make sure the types are the same, and then we do a simple parameter match. Now, I was editing the video yesterday. I don't think I went over this function. So we basically just, pass both the parameters of both functions. So we get the parameters out of here and the parameters casted from this field thing that we passed in here. And we call this function. So yeah, for some reason, I don't think I went over this. And sorry guys, I film this at like 1 to 2 in the morning every day. So I'm usually pretty delirious. Sorry if I'm like going over stuff that we already went over. But as you can see, we basically just call equals on the U types or on both the fields. So that's going to call this equals function, which is what we're going over now. And that's how you do a simple parameter match. So if the left parameter equals the right, then we're all good. So let me go back. All right, so we do that. And we also do it down here. Now, I think the reason why I broke this out, because this code looks very repetitive, I think I broke it out because lambdas, there's a potential that it doesn't have a return type yet because it's a lambda and you're not required to have one. So I think that's why I broke this apart, but yeah. So after that, I just kind of explained this. So if it's not a function pointer, we just return true. And where's the last one? So we have is related. So this is the last function for field. We have basically if both array values are the same, so either both are arrays or both not arrays. And if that's not equal to true, or if they're not equal to each other, then we return false. And then we check for all the various types. So if we have both fields, or at least if the left field is a class, then we check to see if the right side of the field that we're processing is a class. If so, then we cast the field that we're passing in to a class and we check to see if they're related. Now, here is something very, very important that I want you guys to realize. If you notice here, I'm not saying if this current, I'm not getting the value or casting the class value of the current U type and saying, is it related to this field U type? And there's a very good reason for that. So here, I'm going to go to my syntax file and we can where is it at? So I'm going to go to my syntax file and here, I'm going to write up a quick example. So let's say we have a class called A. Create a class of A and we say A is equal to new A, right? So we create this class of A. Then we say we have a class or we have a field of B and B is of type object. We assign object to A. Now, if we assign A to B, this obviously will cause an issue, but it won't cause an issue if we didn't do it a certain way. So here, let me explain what I mean. When we are comparing classes to see if they're related to each other, if I were to say if the current class that we have is related to this class, and actually, you know what, this is a bad example. Let's say, all right, so I'm going to create a class. Sure, I'm just doing this like impromptu. So let's say B has a base of A. Here's a better example. So we have B. So if we create a class of A, we also create a class of B. We can't assign B to A, but we can assign A to B. And if we were to go with this example where we say, in this example, this is broken, right? So this is wrong. Well, how is our compiler going to figure that out? Well, we're basically saying if A is related to B instead of is B related to A. Because when you think about accessing this from a memory standpoint, it's one thing to assign a bigger object to a smaller base object than a smaller object to a bigger object. And how that works, or what I mean by that, is if you have like a field in here, so you have like fields in here and you have fields in here. Well, let's say this class has like, I don't know, 3 fields or 1 field. Let's say it has 1 field. And let's say B has 2 fields. Well, if we try to assign B to A currently, and then we say B dot, second field inside of the B class, that's not going to be possible because we're assigning it A and it only has 1 field. But if we assign A to B, well, A has only 1 field, but the B class has a total of 3 fields. Because when you map this out in memory, you have a total of 3 fields because you have to add the fields from here. So it makes sense from a memory standpoint to basically assign B to A because it's a bigger object. I know it's a bit confusing, but we'll see more of that later on. But just want to point that out. We also have a check for object. So for objects, we can assign a few things. We can assign it, so we check to see if, the type we're assigning is a class or it's an object. If so, we're true because they're related. After that, we have a var. So if it's, any one of these, so if it's actually, that is not necessary. So if it's a greater than, yeah. So if it's less than or equal to a var, then we say that they are related. If it's a function pointer, then this is basically exactly the same code we just went over. Yeah, it's literally the same code. So I'm not really going to go over it. You can just copy the same code that we wrote up here. Exactly the same stuff. And then we have down here, because you can't really, like, you don't want to do like is related checks and like have weird stuff going on with function pointers because they always need to be exact. There's no leniency when it comes to our compiler allowing us to like mix types together for function pointers. So finally we have, our int 8 to int 64. And then we basically check to see if it's less than a var. So you know what? I'm just going to do this. I'm going to say if the type is less than or equal to a var. Well, no, that's not going to work. Okay. I guess that's why I did that. So I segmented it out because if it's equal to a var, then, we can assign it anything less than or equal to a var. And if it's, between these values, so between this value and this value, we assign it to or we can assign it anything less than or equal to a var. You don't want to like just do a blanketed statement because obviously we would be skipping this if statement here by saying, this right here, if that makes any sense. So after that, we have methods. So let's look at functions. Now, when it comes to functions, oh man, functions are really complicated. All right, so here's the imports for functions. I import data entity, field, function type, and code holder. Functions have a ton of things, so I'm just going to skip all the really complicated stuff, and let's just look at the simple like data structure, and then we'll branch out to more complex things. So of course we have, method, basically taking a public data entity as a base class. We create our standardized empty function or empty constructor, and we set up all of our values. So initially, you're going to start out as an undefined function, and of course, we support operator overloads. And what this is this is just a character. And then, we have our extension functions set to false, and of course, our delegate address set to false. So we have our function type, which we already went over. That's the type of the function. Then we have overload. So if this is a operator overload, is it plus, minus, whatever. Then we have our extension function. So that's going to represent whether this is an extension function or not. Delegate address, delegates, the basic principle, the high level, like 5-second answer for how delegates are going to work is, let's say we have a function in B, or let's say we have a function in A, right? Define work. And we want to create a delegate function that we want to delegate work to another class. So that's going to force B to implement work. So we're going to have work here. And what's going to happen is when we call this work function, so like let's ignore the broken code. Let's say we create, a class of B. Let's say we have B is equal to new B. And then we say A, class is A. And we assign A to B because, again, the memory model works that way. It'll allow us to do that because we're assigning a bigger object to a smaller object. So we say A.work. What's going to happen at the low level is we're going to basically have a delegate address attached to this function, and we're going to inspect the object at the low level for every single function that has a delegate address attached to it. So what we're going to do is we're going to add some metadata and say, delegate function, and we're going to reference A.work. So this is kind of how like our compiler is going to do it. We'll see how we attach logic for figuring out which functions pertain to which at a later date, but let's go back. So we have that. We have the type of the function or the return type. We have a list of fields, which we just went over. The field data structure, which represents our parameters. And then we have our code data. So let's look at more functions here. So of course, we're going to have our standardized initialization that we call in the compiler for creating methods. So we're going to pass in the name of the method, which module is defined in, the owner of the method, the standard or the GUID, which is basically the serial number, any parameters that we're going to be processing at the high level. Before we call into this, we need to process all of our parameters, whatever flags that this function is going to have, and its metadata. So where is it defined? And as you can see here, I don't do much for, initialization. So, I set the function type equal to undefined. I'm going to have to do this outside of this constructor to set what function type it is because this is used all over the place. And I don't want to just kind of set it here. So, of course, I probably could have just passed it in here. I don't know why I didn't do that, but whatever. So you can see here, I do a bunch of stuff to set up our information. So you can just kind of copy that down. And as you can see, I have some code for checking to see if, this is a static function. So if we have the static access flag in our list, then we basically say this.data.local variable size. Now, where is data? Is that where's that at? Code, okay. So that's I thought this was code holder for some reason. So create this data structure code data. We're gonna go over that in a few minutes. But yeah, so this is where it gets into, it starts to become very complicated for especially me and for you guys as we're building the language. This is something that's kind of forward thinking. I've already built my virtual machine, I'm already testing it, so I understand how it works. The reason why we want to do this and what this is doing is we start out basically with every function having a certain amount of variables, right? So each function is going to have a allocated stack size for when we call the function, how much stack space is it going to require? And if it's a instance function, well, we need whatever the parameters is plus one at a minimum for our stack size. So if we have a function with 4 parameters and it's an instance function, we need a stack size of 5 because we have to pass in the instance to that function. So that's all this is doing. We'll see more of that later on. As you can see here, I allocate 1 slot for the class instance. So just copy that code down. I don't want to go too much into detail on that. So let's kind of scroll up, or let's actually finish some of these functions first. You can see I have a copy, which basically calls the data entity copy, which copies that data, and then it copies the same elements here. So, it copies whatever fields we have into this method. Let's see. So we have free. What does this do? Does this not work? Okay. All right, I guess it just didn't let me go in. So I call release, and then I call compiler free list pointer. This is a function. So I have a couple different functions here. You guys can copy this down. Basically, it's just a quick way of freeing data. So if you guys are using the list that I created, my custom list file here, where I can do a bit more fancy things than the standard std list in C++, then you can kind of copy these functions down. It just for loops through the list, frees up each element, and then calls, the final free on the list that we're processing. And of course, I have, another function called free pointer. We just pass in a pointer. It frees up. It calls free on that object, and then it deletes it. So that's kind of like, I have all these free methods for fields, methods, classes. So I use that function as well in the compiler. So let me go back here. So yeah, so I call free list pointer, and then I check to see if the return type of this function is not equal to null. If so, free up that and then delete that value out of memory. So after that, we have a toString function. So we basically just say, it's a function, and this is how I got that pretty error message that I showed yesterday. So we have, if our function type is a delegate, then we say, delegate before the name. And then otherwise, if it's not a delegate, we check to see if it's a function pointer. If so, we put like the pointer symbol to denote that. And then we check to see if the type is not equal to a function pointer. Then we put the full name. Now, the reason why you want to do that is function pointers typically don't have names, so it's just going to be blank anyway, so I just don't have a full name there. And after that, we basically print out each parameter, and then after that, we check to see, if we have a return type, we put the colon here, and then we print out, or we call utype2string. Otherwise, if we don't have a return type, then we say untyped on the return string. Now, the way we print out the parameters is this is why we have the toString function and fields. So we put a left curly brace and then or a left parentheses, for loop through the parameters, call toString on a string stream, put a comma. And here's how I check to see. So like, here's how I make sure that, I don't put too many commas or commas in the wrong spot. If we have another parameter to process, so if we say if I plus 1 is less than parameters, the size, then that means we have another thing to process. Then I basically just, add another comma. After that, I close it up and I return the string. So that's how I print the values of methods. And yeah, so that's pretty much all the functions for processing a method that we're going to need. And finally, we're going to need code data. Code data is a really complicated like memory model, or I guess data structure. So this is what I use for compiling this function. So this is all of the code data that my compiler is going to need for processing and compiling functions. So what you're going to need is you're going to need a code holder. After that, you need a local variable size. This is going to represent the total stack size of our function. As we're creating variables and local variables in our function, we need to allocate another stack slot. So we're going to keep track of that using this. We have a list of fields called locals, so that's what that is. We have trycatch data, and all these data structures are above, so we'll just go over it, but you can just kind of copy this down. So we have our trycatch data, or our trycatch table. We have any local aliases that we create. We have a label map for any labels that we have. We have a branch table. We have a protected code table, and we have a line table. So let's kind of go up to kind of see what these various things are. So line data, what is that? Let me go back here to my ODF file. Oh, why did it do that? Did I not? Okay. So if I go back here, and where was that? I was at method.h. Where's that at? Here. So if we go back to our label data, you can see here that, oh, I thought this was line data for some reason. That's weird. Okay, so this is how we keep track of labels. I guess we'll go over line data in a little bit. So we keep track of labels by basically, saying where does the label start. So like, let's say we have a label right here. We keep track of where that data is started. And of course, we started out with a invalid address if we don't have, or if we call the default constructor, we say, no name and scope level is -1. Now, I will mention something. Labels die at the scope that they're created in. So if you have, like, for instance, if you have, a function here where you have if, true or whatever, right? And then we say, work or some label, and then we, go to some label. Now, imagine that you're doing something here. So we're doing some other stuff. We have some other code, and then we, say go to some label. If we go out of here, out of the scope of the if statement, and we say go to some label, it's not going to be able to jump here because it's out of scope. So, and there's a very good reason why we need to do that, because if you have go-tos inside of finally blocks, you need to be able to guarantee that the finally will execute. So, yeah, that's what that is. But that's why we have that. So next we need to create our constructor that we're going to call in the compiler side. So we basically, say the name of the label, we're going to say, the start PC and what level of scope it was created at. So as you can see here, here's a quick explanation. After that, we have our branch table. So this is how we're going to keep track of, like let's say, I don't know, here, if I go back here, right, if I have, this code here. So I have this code, or I have this label, and let's say, there's some code here, and this label's doing some work. And, let's say I have some code in this if statement. If I say go to label, at the current time of processing this information right here, this label doesn't exist. So how do we figure out where, where do we need to jump to in order to process this label? Well, what we do is we store that into what's called a branch table to basically say, all right, I'm going to put a pin in this. I don't know exactly where this label is defined. So just put it in the table and resolve that data at a later date, which is totally fine. So we're going to need to have that. So in there, we have a couple different things. So we have resolved. So as we're processing our branch table, we're not going to clear it out. So kind of like how we clear out, our label data or our label table every time we exit scope, and whatever scope level you're at. So like if this is level 0, this is level 1. Any labels created at level 1 will be purged, and any data once we finish processing this function created at level 0 will also be purged. Even though that's the case, we don't want to do that for branch tables, because at a later date in our code, we're going to have what's called a code optimizer. And in fact, I'm actually working on it right now. I'm doing tons of stuff. But we basically want to still be able to keep track of where all of our branches are, so that way we can do what's called, here, let me see if I can find the function. Yeah, So basically, every time you have here, I'll do a quick example. So let's say, let me find a good one. Okay, so I had this stupid bug where I had, in my compiler, take the value in this register and move it to here, and then like just do the same thing again. Like that's really dumb. I'm not effectively doing anything at all. So I basically remove both of these instructions. And when I do that, I need to shift all of my addresses that I was processing. This is really advanced too, by the way. I hope I'm not boring anybody to sleep with this, but you just want to keep it so that way later on we can just for loop through the branch table and update any addresses. Like, if we have like conditional jumps and stuff like that. So we're going to need to know where was it, where was the branch initiated, what was the label we were trying to go to at the time, any offset that we have. So like if we were going to offset the address at a certain number of, whatever, what was the line and column, where did it happen, and what was the scope it was defined at. Of course, you want to create your free function as well. And yeah, so let's go up. Next, we have our trycatch data. So we're going to want to have, we're going to have a try start and end and a block start and end. So here, I'm going to go back to our syntax. So if we have like a try catch, or actually, you know what? I'm going to go here. I was actually doing some pretty interesting work on my exception system. So I've been thoroughly testing my exception system. And here, if I uncomment this code, basically, like this is ridiculous. No one's going to do this, but basically what you want to do is you want to have two different types of PC trackers for your, try catch. You want to have where did the block start and end. So the block start and end is going to represent this, and the try start and end is going to represent everything inside of the try. The reason why you want to do that is if you throw an exception here, you're inside of this block, totally fine, right? We can throw an error and then catch it. But what happens if you throw an error inside of a catch? You still need to execute this finally, so we want to still make sure that are we technically still inside of a try catch? If so, then we want to basically jump to the nearest finally block and execute the data. Again, very advanced, but we'll go over that later on. So you want to create, all of these, and you want to create a list of catch tables for our try catch data structure. And then you want to create a pointer to finally data. Now, the reason why it's a pointer is because not every try catch has a finally block. And yeah, so if this is null, then obviously we don't have any finally data. So if we go up, now we have a thing called ASM data. Now what this represents is, let's say, in your code, as you can see up here, I have an example where I'm like printing. This is like a low-level version of printing a hello world, or printing anything to the console, really. So what I do is I load the value of, this character from the message array that we passed in as a parameter, and I just call putC, which puts a char to the console. This code is literally going to be injected into this function, but there's a problem with that. When we have our code optimizer, the code optimizer doesn't know or have a concept of, this code that I wrote here was written by me and not by the compiler. So we basically want to say, here's the start and end of any ASM data that I wrote into the function. That way the compiler optimizer doesn't override that information. So I actually have like a function check in here or something like that. What is it called? It's called inside protected code base. So yeah, it's just gonna for loop through the protected code base, which represents the ASM data, and it just makes sure that the compiler doesn't like screw up the code here because it's trying to optimize the hell out of everything. Eventually, I'll have at least like 40 optimizations. Right now, I have like 4 or 3, but eventually I'll have like 40, and we just want to make sure we don't do that to the user because that's bad. So yeah, just create those, and of course, create an equals operator. If you pass some data in, you can copy that data down. After that, we have our line data. So I'm sure you've seen it before, but like here's an example. So we have like our SRT init, and if I put this side to side, you can see here that at line 23, SRT init, this is the start of the for loop. So this was with the code commented out. This was without all the, try catch stuff. This is how a for loop looks, at the low level. So at line 23, we have the start of the for loop, and this is all this stuff. And then at line 46, I have, return value returning some data. So since all of this data for processing is basically on the same line, it's all going to be encapsulated within there. But we want to keep track of, where we are in the code, so that way if we have an exception, we can, print it out. So let me go back to methods. Also, I'm mentioning a ton of stuff, so if you guys have any questions, of course, just put it in the comment section below. So let's kind of see. All right, so for line data, you want to create your standard instruction or your standard constructor here. Then you want to create your constructor where you pass data in. As you can see, this is what we have, and then we have an equals for line data as well. So for line data, you want to say where does the line start, and you also want to say, what the line is. So if we go back up, or if we scroll up, we have now our finally data. So for finally, we're going to create, I don't even want to explain that. All right, so just create this. I would have to explain my entire exception system to explain why we need that. I'm not even going to do that right now. Don't feel like it. So that's too much information. Just create this exception object field address and create the start PC and end PC. So after that, we have our equals, where if we, pass a finally data in here, we just, copy the data down. Of course, we have our empty constructor. Finally, we have our catch data. So this is where if we catch an error, this is how we catch, or this is how we keep track of, catching information. So we have a handler PC. So, where in the code did the start of the catch happen? So here, I'm actually, you know what? I'm going to do this. I'm going to comment this code out. Okay, that doesn't work. I'm going to put a trycatch here. So I'm going to say try, and then I'm going to say I is equal to 0. And I'm going to put a catch of error, ERROR, and put, I don't know, let's put like a throw or something. Let's uncomment that out, throw new error. All right, so here we have a example. So if we go here, and you know what, what's interesting is we can actually see how this data is processed by the compiler. So I put a bunch of like helpful things here for me to just see what's going on as I'm writing my code optimizer. But as we can see here, right, if I put this side to side, it's going to give you guys like a quick looky-loo into how the code looks. So we can see here we have, I store local, and we basically store 0 into frame pointer plus 1, which is the address of this I variable. And you can see here immediately after that, we jump to 9. So we just jump over this catch, because obviously if there's no exception, we don't need to catch anything. So that represents the end of the try block, which, just before we jump over this catch, that's the end. Then we have, this catch portion here. So we catch an exception. And if we look in, where is it in? It's in my errors, exceptions. You can see here that exception is also, represented as an error alias. So that's why it's std exception. And we have our error here. And this is the start PC. And then we have the try end, which represents the end of, this try catch. So you just basically, create a new class, throw the error. So that's just kind of, it's really cool to kind of see this stuff kind of come together. But as you can see here, all we need for catching exceptions is we need, where did it start? What's the local field address? Now we need a local field address because, like, let's say E of error. If we want to basically have the value of the exception that we're throwing or that we're catching at the low level, we need to assign the value of whatever the class is that we're catching to this local field. So we need to know what the address of it is to assign it. And then we need to know the class address. So that represents what are we catching. And as you can see here, we have the same standard functions that we have everywhere else. We have a basic constructor here. We have a init function here, which basically just takes, we do the same thing we do in here. And then we also have a free function, which does nothing. I guess I'm calling this inside of the free list pointer or whatever that I showed earlier. Then we have an equals, so that basically just copies the values from another pointer, and that's it. So that is how we set up methods. Now let's kind of look at what else. What else do we have to do? How long is this video? Is it super long? Okay, yeah, it's pretty long. So if we look at class objects, now this is the absolutely last thing that we need to do. Classes are huge. There's tons of stuff that we need to do for this. So where do we start? So first we're going to have what's called a generic processing stage. So as we're processing generic classes, there's going to be stages that we can do certain things and we can't do certain things. Because generics are a very pesky and annoying thing to process, you can't just process all things inside of that class at once because you'll cause seg faults and compiler errors because you're trying to access data that's not there. So in order to alleviate that, we have a stage of unprocessed, created, pre-processed, post-processed, and compiled. And those are the various stages of processing a generic class. So if we go back down, let's see what other fields we have. We also have whether or not it's a global class. So that's going to be if it's the SRT global. And then we have, our class type, which is just a integer representing, where's that at? Is that in here? Yeah. So we're going to have various different types. We're going to have normal classes, interfaces, generics, and enums. So those are going to be the various types. And by the way, this is bit shifted. I actually took the time out to bit shift this. If any of you guys haven't really worked on bit shifting before, I would definitely recommend checking out some tutorials on bit shifting and C++. But as you can see here, we have, if it's a normal class, it's just 0 as the class type. But we can also have, a class that's both an interface and a generic class, or a generic normal class, or it could be an enum, whatever. So there's various different types of classes. We can have more than one type. So that's why it's, staggered in this bit pattern here. And if you guys remember before, this is one bit, this is another bit, and another, and another. We go back down, we have what else? So we have functions. We're gonna have a list of functions, and it's just gonna be one list. So if you remember, each function has its own type. So we can just do a search for the type of the function that we want to process. So it's gonna be really nice. We'll see how to do that later. We also have a list of ASTs of extension functions. These are going to be where each extension function was found when we were compiling our code. Again, we can't process everything at once, so we're going to process extension functions later. We also have a list of, class mutations as well. So any class mutations we have, we want to store where those were encountered so we can process those later. We also have, what is this, classes, so any subclasses we have. So this goes back to that dependency graph that I was talking about in a couple videos ago. This is how we're going to basically graph out our classes, right? So every class is going to have a list of subclasses, and we'll just process it that way. We also have a list of aliases, a list of interfaces, a list of fields, a bunch of keys. What this is this is like, for instance, if you have a generic class, and I'm sure you've seen it before, like if you have a class generic, so if you say like gen of type T, so this represents a generic class, and these are the keys of that generic class. So we just want to map out the keys in here so that way we can process it later. And then we have a list of U types, which represent key types. Now here's where you're going to start to see how powerful U types are. It's very easy the way I do it. Literally, I just map the keys with the pointer of U types. And if you remember, U types are everything. It's fields, it's methods, it's everything. So it's going to be really easy for us to process data on the compiler side. After that, we have our super class and our generic owner class. This is so we can make a reference to, what the, whoops, I deleted it. This is so we can make a reference to what the generic class that we created is. So like, for instance, if we create a new gen of type var, this class theoretically is no longer just this generic class. It's a completely separate class than this, at least as far as our compiler is concerned. So we just want to create a function or a field so that way we can, know what that is. After that, we have processed extension functions. So this is going to be a long for how many extension functions we've processed, because we're not going to process every extension function at once. They're going to be staggered. So, that's why we have that. We just want to keep track of how many we've done. After that, we have how many mutations we've processed. Same concept. We're not going to process all of them at once, so they're going to be staggered. So next we have a transfer. So the way we're going to process generic classes, we're not going to okay, so let's say we have this field here, num of type t. When we process this on the compiler side, here, you know what? I'm just going to do this. It's going to be a lot easier. So if I go to compiler, I'm going to go to compile. If I go to preprocess, and as you can see here, if we try to preprocess a generic class, this is very empty. So I'm not going to explain what this function does, but if we look at this versus preprocessing a regular class, as you can see here, when we preprocess a regular class, I go through all of the data inside of that class. So I preprocess any aliases that class has, any local variables, I preprocess any subclasses it has. So you can see I do all that, right? But if I go back to preprocessing a generic class, if I scroll all the way to the bottom, it doesn't do anything. And you can see I have a message. The purpose is to simply create the existence of the generic class, and we will process it later. So we want to have this transfer function because we want to just get the crucial information that we need for that generic class once we actually create it. So when we create the basic form of a generic class, where the heck is that? Okay. So once we create the generic form of it, we're going to have, what superclass does it have? So if it has like a base class, base of, I don't know, string or something, I don't know. And then so we'll have that, we'll have its processing stage, and just, you can copy this down. But these are all the basic fields we need. But if you notice, I don't have anything in here like, what aliases does it have? What fields does it have? What functions does it have? Because none of that data is processed at the time of compiling that generic class. So you can freeze the screen or pause the video and basically copy this down. After this, we have, a getChild class function. So all this is going to do is we're going to take a name and we're going to check to see if we have a match. Now, the reason why I want to have this match boolean is for when we have an error, if we try to resolve a class or a child class and it doesn't work, we will basically complain to the user that we found similar classes with the same name or similar names to it as an error in the compiler. So we'll see that at a later date, but basically all you want to do is for loop through all of the classes and check to see, get the index of, I and get the name and check to see if the names are the same. Otherwise, if match is true, then we also want to get the name and we want to call find. And what that does is this is actually a string method in C++. And if it's not equal to n position, that means that we found this string inside of that name. So like if we were trying to, create a new n of var, then the compiler is going to realize that this is a typo and it's going to say, did you mean gen? So yeah, this is just an example. I know this isn't a subclass, but it's just an example to explain how it works. So we have that. We have get functions by type and name. So we're going to pass in a function type, and this is how we resolve functions at the compiler level. So we pass, what type of function we want to resolve, and we say, what's the name of the function, whether or not we want to check the base class, and we pass in a list of methods, and that's going to be the results. So as a function, the way we're going to compile functions is we're always going to get the names of the functions that we want to process first, and then we want to try to resolve that function to see if that call to that function is potentially ambiguous. So we don't want to just outright say, give me this function with these parameters and these values. We want to get all of the functions under that same name or under a similar name, and then we want to process it that way. So we just for loop through it. We check to see if the type of the function type is the same, and then we check to see if the names are the same. If so, we add it to the results. And then if we want to check the base class and we have a superclass, so if superclass is not equal to null, because theoretically it could be null, like if we don't have a base class, then we just call the same method on that superclass. And of course we pass true for check base because obviously it's true if this is true, so we don't need to pass in whether or not it's true. Next, let's scroll up. So next we have, do we have an interface? So we're going to pass in a class object, for loop through the list of interfaces, and check to see if the class matches. After that, we want to get all functions by type. So we're going to pass in a function type, and we're going to pass in, a result, reference to a list results, and we're going to, pass in whether or not we want to check the superclass. And we're just going to for loop through the function, check to see if the type is the same, add it to the results. If we want to check the superclass and super is not equal to null, we call this value or this function on the superclass. After that, we have total interface count. What this does is this just gets the total amount of interfaces all the way dated back into each superclass. So this function is mostly for building our executable. Basically what we do is we just, get the current interface count by how many interfaces we have. We set the current class that we're going to process to the superclass of the current instance, and then we, check to see if it's not equal to null. So obviously superclasses can't be null. So in this instance, if we call this function on here, it'll just stop at this point and just return the value that we generated up here. Otherwise, if we have a base class like string, then it will go to, like, if string has any interfaces, it will get the interfaces from that class as well. And then what we'll do is we'll just set class equal to this value, this temporary value, and then we'll just keep doing that until we run out of superclasses. After that, we have, get class mutations, which just gets a reference to the list. We have, okay, so we have a bunch of getter methods. You can just kind of see what those do. After that, we have, set interfaces, so we can pass in, which interfaces we have as a class. We have set generic owner, so, when we're actually compiling generic classes, we want to set the original generic class reference, so that way we can process that for later. We want to get the generic owner, get the child class, get the total amount of functions, get the total amount of aliases, get the total amount of key types and keys. Now we have a bunch of other functions. We can add, key types. So we want to add all of the types of our keys here. We want to add the string values of our keys. We want to get the total function count in this current class. We want to add a single function. We also want to add a field, and we want to be able to add a class. Now we have we have a bunch of functions. So we have a couple other functions. These are also for creating an executable. So if we go here, this is basically the same thing like processing interfaces. We just want to get the total amount of functions that this class owns. So we get the total amount of functions that this class specifically has. We get the superclass, add it if possible, and we just keep, getting the superclass until it's null and just return that value. Same thing for, or this is kind of different. So this is for static fields. So basically, we'll go over how our class memory model is going to be mapped later on. But basically, this is for generating addresses for fields. So we call get total or get static field count. So what that does is that just basically for loops to all the fields, checks to see if it has the static flag, and increment this long here, then return the value. So that's going to return how many total static fields do we have for that specific class. Then we just keep doing that for each superclass, rinse and repeat until we run out of superclasses. So if I go back, same thing for instance fields. It's the exact same thing. We just create a long, check to see if it's not equal to static this time, and if so, we have an instance field, return that value, and then we keep doing that until we run out of superclasses. After that, we have total field count. So we kind of, did we go over this one? I don't even remember at this point. It's like 2 in the morning. So we basically have our field count here, which is our total field count, and we just keep doing that for the base classes, same as we've been doing for all of the other functions. After that, we have get alias. So if we want to get an alias at a specific name, and we want to potentially check the base class, we for loop through all of our aliases. We get an alias, make sure that the names are the same, we return the alias if they're the same. Otherwise, if we want to check the base class and we have a superclass, we just call this function in that superclass. After that, we have get field index. That's going to get the index of the field in the specific class. So, we for loop through the fields, make sure the name is the same, and we would just return whatever the iter is. You know what? Why don't I just return I? I have no idea. This is completely pointless. You can just return I if you want, but yeah. So after that, we have get static field count. So I think, yeah, we went over that. So this just gets how many static fields we have. This gets how many instance fields we have. This gets a static field address. Now, this is how we're going to get the addresses of our fields. Again, I'm not going to go over how the memory model is laid out, but we need to create this function. So we basically say, string name, whatever the name is, and then we call get field index. And what that does is that just, as we saw, get where the field is located inside of the class. And then once we have that index, we go for that amount of indexes and check to see and how many static fields we've processed. After that, we have a getter function to basically get the instance field address. So if you noticed, static fields and instance fields have two different types of addresses. In short, without going into too much detail about how the memory is mapped out, we basically separate the addresses of both static and instance fields to save memory. That's all I'm going to say about that. So what we do is we just check to see if it's not a static field. If so, we just, keep adding up the addresses until we run out of the instance or the index of that field. After that, we have get field address. And this function basically, I mean, you can kind of see it here. All it does is it just checks to see if we have a static field. And, if the super is equal to null, then if the field is static, we just call get static field address. Otherwise, get instance field address. Now, this is the actual getting the address of the field function. So it does this automatically whether or not the field is static or not. We get the address by basically getting the static address of the field in this class, then adding up the subsequent values in the superclasses. Of course, if we have like, a field in a superclass, like if we have, three fields in here, the address of this num value is not going to be 0. If we try to like, so if we say gen of type var, and let's say we have, v as the variable name. If we say v dot num in and we say equal to 10, when we try to access this field, it's not going to be at the address of 0. If this has two fields in it, this will be at the address of 2 because 0, 1, and then 2. So it's going to be the third address in the class. So we have that function. Let's see what else. So we have, get function by name. All you do is just pass in a name, pass in a function array result list, whether or not we want to check the base class, for loop through the functions, check the name, add it to the results list, and then check to see if we want to check the base class, and then we do the same thing. And in this one, we return a Boolean, unlike other functions where we're returning void, and we return whether or not, the results list is empty. After that, we can set whether or not it's a global class. We can check to see whether or not it is a global class. We can set the processing stage. We can say, this is a is not function. So what this does is when we're processing classes, we want to see if a class is either not something or is at least something. So when we're trying to process or do something specific, we can say, is the class at least pre-processed? And what that does is that just checks the processing stage. And if the stage is greater than, the current processing stage is greater than the stage that we're passing in, that means that we are at least that stage. If we want to check to see if it's not a stage yet, then we check to see if the processing stage is less than the stage we're passing in. So there's that. We have, we want to check to see if a class is related. So I actually think we've gone over this one before. Yeah, I think we went over this one in a previous episode. So I don't have to go over that. We have get superclass, set superclass, set the class type, get the class type. We can get a function at a certain index. We can get a field at a certain index. We can also get a field at a certain name and check the base class. So if we want to get a specific named field, then we just for loop through the list. If we have the name, we return the field. Otherwise, we check to see if we have a superclass and we want to check the base class, and we call the same function. Finally, we have field count, which is just the total amount of fields we have. And after that, we have free. All this does is it just calls a bunch of free list pointers. So we call release in the data entity class. We call keys.free, which just frees up, our string keys. And we just call free list pointer, which basically just calls free on every single element and then calls free on the list. And we do that for fields, classes, key types, and functions. That's why all of these objects have the free function inside of them. So that way we can just do that and like release all the memory. So let me scroll back up to the top. Let's see what else we have. Match. Finally, we have our constructor. So this is going to be it for object-oriented. Definitely happy that we've gotten that out the way. So you basically want to, whenever we create a class, you want to set some basic default values, as you can see here. And then, of course, you want to initialize all of our list items. Way down here, you want to initialize all of those. The only thing you really need to set is the name, what module is defined in, the serial number, any flags, and the metadata. And yeah, I'm pretty sure. And of course, you want to set the type as class. Obviously, we know like what the data type is inside of data entity. So we don't need to say, you don't need to pass the type in here. We just say it's a class. So that's going to be it for today, guys. I know that was a lot of information, and yeah, this is a pretty long video. So tomorrow we're going to talk about how to set up our code obfuscation system. There's still a lot of stuff we have to do before we can even think about writing a single line of code. But once all this is done, it's going to be very easy, well, relatively smooth to kind of go over everything else. So as usual, as I mentioned before, if you guys have any questions, definitely put them in the comments section below. And if you guys would love to help support the channel, definitely head over to my GitHub repository at androidevcd/sharp. And when you do, definitely watch, start, and fork this repository. That's going to give this repository a lot more visibility and let other developers know this language exists. Also, if you guys are curious about learning what I've been up to on a daily basis, you can head over to the remastered branch, and I write some pretty wordy commits, so you can kind of get a gist of what I've been up to without really having to look into the code. And of course, if you guys are curious about learning maybe stuff that I'm looking to do in the future for this YouTube series or stuff that I've done in the past with this language, you can check out the docs folder. And there's two main files. You can check out the change list, which represents all of my previous updates for previous releases. And the roadmap contains all that information as well as new stuff that I'm looking to add in the future. So that's going to be it for today, guys. Of course, if you're new to the channel, definitely consider subscribing. And until next time, I'll see you guys later.